All right, so we're live. Good. We're going to do some physics problems for several days. So I have a quiz here. What do you know about physics? If you could please let me know. There's some important formulas here. We'll go over some of those. And then the rest is more educational about force, pressure, and work, which are things that we're going to start playing with. So please check that out. What's that? Force, yes. All right. Quiz 3, I meant to have due last Friday, but apparently I can't tell time because I entered the 15th instead of whatever last Friday was. That would have been the 8th. So please turn it in as soon as possible. Like today would be great because we're moving on to new stuff, and that's about volumes. And the big thing about that quiz is I want you to draw pictures. So draw the region in the XY plane. Draw the little rectangle that's going to be revolved. Label its thickness as dx or dy, depending on whether you use shells or disks. And then you're going to come up with an answer. So please do that as soon as possible. And if I emailed you saying, hey, where's your quiz? I was expecting it last Friday. My apologies for my mistake and my email. We're in chapter 2. We're going to take a quick look at surface area again and relate it to a volume problem. And then we're going to jump into physical applications today. And which is why I'm asking you about your physics knowledge.
This is classic physics, or getting the fluids?
Pretty much just classic fluids. It's too hard to get anything into complicated fluid type stuff. We're just going to keep it pretty simple. And so we're going to do a little mass versus density. And there's a couple of those. And then we're going to talk about work. And is that it? Work. Oh, and force and pressure. So those are the things that we're going to play with. All right, back to my favorite place, one of my favorite places in the world, Wikipedia. So there's a thing called Gabriel's horn. And it's called Gabriel's horn in honor of the Archangel Gabriel. And it's an infinitely long horn, right? So human beings can't possibly possess an infinitely long horn, so hopefully Gabriel can. And this horn is made by rotating the function y equals x around the x-axis. Okay? Now, if you make such a horn, we started building a finite one in class last time, and we'll come back to that later. So if you just say stop the horn here, maybe you went from 1 to 3, and you rotated that and made a horn, you could fill that horn with liquid if you capped one end, right? Or you could paint it because it has a surface area. So what we're going to look at is the difference between filling that horn with something volume and painting it surface area. Okay. Now, if you make it finite, it's no big whoop. We can totally do that. We can calculate it. The interesting thing happens is what happens if you let that go out forever. You have an infinitely long horn. Okay. See, did we do oh wait, no, this is Calc 2. Wait. Yeah, we haven't done it yet. So a topic we're going to get to later is the idea of an improper integral. And an improper integral is an integral that's not proper. Well, how does it become not proper? It becomes not proper if you try to integrate with infinity. Okay. So for example, what if we tried to integrate from -1 to 1 here? What problem do we have? It's broken, right, in the middle, and there's a vertical asymptote. So if we were to integrate, one way to interpret this is that that's the area. And this thing goes up forever, right, without touching? So is there infinite area in there? Okay. Maybe. How can you say for sure? Just because it goes an infinite distance. So for example, is it true that we take limits, and sometimes limits as x goes to infinity turn into some number like 0 or 1? Mm-hmm. Yeah. So it's possible that you could have an area that is infinite in size, because one direction goes out forever, but it can close off fast enough that it has a finite amount of area, which is wicked bizarre. We're going to play with that idea later in the course. I just wanted to give you a quick snapshot of it now. So back to Wikipedia. We're already there. All right. So here's people at Wikipedia were nice enough to actually solve the volume integral for us. Let's see, does this volume integral make sense right there? Pi. If there's a pi involved, which method do you think they're using? Disks or shells?
Disks.
Disks, that is correct. And then they have something squared, which should be the radius. And the radius here would be our function 1 over x. Okay, that seems reasonable. So they have pi times the radius squared, and they integrate up to some value a. Okay, a could be 2 or 3 or 4, or it could keep going. Now, if you solve this, what you're going to get after you evaluated that a and 1 is you're going to get 1 minus a is the antiderivative from 1 to a. And if we let a go to infinity, what's going to happen here? What's 1 over a as a goes to infinity? It goes to 0. It goes to 0. So what's the volume of this object? Pi times 1. Okay, so I'm just going to sketch that out quick, what we just did, or what Wikipedia helped us do. So we were looking at Gabriel's horn. Just to wrap our minds around where the horn comes from. So that right there is the function 1 over x. And we're going to rotate that function around the x-axis. If we use the disk method, disk uses rectangles that are perpendicular to the axis of rotation. So that means I'm integrating with respect to x. There's my little dx on the rectangle. And for a disk, we need pi r squared to generate its area. If we then take that area and we integrate x into it, that gives it length. Area times length gives us volume. So that's the volume, that's a v there. Okay. And we're going to go from 1 to some number a. And it turns out the antiderivative for that is just negative 1 over x. And this cleans up to be, if you evaluate it, 1 minus 1 over a. After you plug in the boundaries and clean up signs. To the chase. Now, if you wanted, hey, if a was supposed to be 3, right, then the volume of the horn would be 1 minus 1/3 times pi. So from 1 to 3, the volume would be, what, 2/3 of pi? Mm-hmm. Right, and that's a horn that looks like this. Got a little blowing end over there. The length of the horn is 3. What's the radius of my horn at the big end? 1. Yeah, that's a radius of 1 at that point right there. And if we were to fill that with paint, whatever the units are, it would be 2/3 pi cubic units of paint, right? So the fun part happens if we let that length go to infinity. So we have this infinitely long horn. And that means we just want to take the limit as a goes to infinity of this pi times 1 minus 1 over a. And the only thing that has an a is the 1 over a. And that limit we just talked about a second ago happens to be 0. So the volume of this infinitely long horn is pi cubic units, whatever the units are. Crazy, okay? That an infinitely long thing can have a finite volume. And it's just because this curve crashes towards 0 fast enough. Okay, if it didn't go to 0 fast enough, then obviously we'd have a different situation here. All right, next story. So Gabriel has this infinitely long horn that has exactly pi units of volume inside of it, which is like, wow, pi. Pi is a very special number in many ways. What about its surface area, right? We want to gold plate this thing. how much gold plating do we need to paint a horn that has a surface that has a volume of pi? Well, this integrand right here is rather complicated. It takes a couple of pages of work to come up with an antiderivative, so I'm going to skip that for now and do that for you in a couple of weeks once we have more tools. But what happens is basically I'm multiplying by this positive constant here. Okay? And because I have a +1 in there, this positive constant has to be a little bit greater than 1. Okay? So that means if I remove it, I get something a little smaller. So all this second integral is the square root is missing. Okay? So if you multiply this by something bigger than 1, you get that. This one actually, what's the antiderivative of 1 over x? Natural log, yeah. So what happens is if you integrate this easier one from 1 to a, you just get 2 pi times the natural log of a. What does the natural log do as x gets bigger? Anybody remember the shape of that sucker? So this is the picture of the horn. It's a picture of the area function. And the area function depends on the natural log of x. And natural log of x does that. And as x goes to infinity, guess what y does? It goes to infinity too. So if you take the limit as a goes to infinity of the natural log of a, guess what you get? Infinity. So this is a very bizarre horn because it holds a finite amount of volume, but its surface area is infinite. It can't hold enough paint to paint itself. What? How is that possible? Infinity is a weird idea. Weird things happen when you mess with infinity. Okay. That's the end of that story. I'll leave you guys to think about the political, religious, and spiritual implications of it. All right. New problem. So we will actually come back to this one later, but we need more tools to do it. So we'll do this one in chapter 3. Physics stuff.
After actually all the stuff.
No, it isn't. I thought this is a more appropriate title. Let's see, what's it actually called? It's called 2.5. Physics applications. Physical applications. Thank you. That's more precise.
Okay.
All right. I can spell physics stuff easier. All right. Topic number 1: density. So density is pretty complicated. We're going to overly simplify it to get a start on it, and you would have to go on in math to do more complicated things with it. So we're just going to kind of take a little bit of bite of the idea of density. So density is defined to be how much stuff is packed into a given space. The more stuff you pack in, the more dense it is, right? So for example, think of a rubber ball versus a steel ball of the same size. If they have the same radius, are they going to be exactly the same weight?
No.
Right? No. So it's mass. Mass is just the amount of stuff something has divided by volume. So that's density. So lead or steel has more stuff packed into a given volume than rubber or carpeting or cloth or something like that. Now, we're going to look at what are called linear density functions. And the reason we have to do that is, in reality, the density of anything isn't uniform unless it's like a pure substance, and it was built very carefully. So generally, something is not going to have uniform density, but we try to assume things do have uniform density. We're going to look at linear density functions because right now we're kind of stuck with functions of a single variable. If we wanted to look at the density of a ball or the density of a plate, we would have to go in 2 directions or 3 directions to talk about its density. Okay? So we'll also talk about an idea called radial density, and we're going to simplify that a little bit. So linear density means we only consider density to change in one direction. Radial density would mean the density changes in concentric circles. Okay? So we might have an object that is maybe more dense in the center and then slightly less dense around the edge. So that's the idea of radial density. And radial density is like a first step at looking at density in 2 dimensions. Okay? But it only changes over the radius. Otherwise, if we wanted to consider like a 3-dimensional ball, when you look at a ball like this, you have a z direction, right? And then coming out, you have, let's say, a y direction, and you also have an x direction. And if reality things aren't uniformly dense, then the density is going to change depending on which x, y, z point you're at. In which case, to kind of add up all of those little dense areas, what's our calculus symbol for adding stuff up?
Summation.
It's a summation that turns into an integral, right? Yeah, so in reality, to look at the density of a 3-dimensional object, you would have to integrate with respect to x, you would also have to integrate with respect to y, and you would also have to integrate with respect to z. So you get this thing called the triple integral that you have to deal with. Right?
Well, that's nasty.
We're not quite ready for that. And then you would, inside, you would possibly have this function of x, y, and z.
Well, we
Right?
end up
And a
doing-
function is kind of a 3rd variable, so we've got this 4th-dimensional idea that we're playing with here when we do that. Okay, so that would be like a course in vector calculus where you would get
good.
something like that. Yeah. So we're just, that's what I mentioned, we're oversimplifying stuff for a more complicated world, but it turns out you can kind of play with it later, depending on what you do. So we're just going to look at the idea of linear density. So what we can imagine is the density we're looking at is maybe the density of a wire. And one end of the wire is not quite as dense as the other end, maybe because of the materials that were used in it. And radial density could be kind of a plate or a disk kind of thing. Right? So those are the 2 kinds of things we're going to mess with for density. All right. So sometimes density is constant. And that constant, right? So we have density equals mass over volume, or if you switch that, mass would then be density times volume. Usually the symbol that's used for density is the Greek rho. And it looks kind of like a curvy P-ish object. So you're going to see this rho symbol pop up here and there, and it's just the symbol for density. And sometimes we can't assume that density is constant, then it's just easy density times volume, no problem. If we have what I call the linear density function, so that means the density changes linearly along a straight line. So that means rho is going to be a function of x. And so maybe we have this very thin rod. So this is like zooming in on a rod. And maybe this is x equals 0, and the x-axis moves through. So that any x value we stop at, some x value in the middle, let's call that x1, is going to have a slightly different density than, say, this other x value over here, x2. But then this circular cross-section I'm making here of the rod, let's say that circular cross-section is uniform. Okay. So if I wanted to take that circular cross-section and turn it into density, then all I would need to know is the x value that I'm at and just multiply by rho. I just want to add all of those up. Okay. So it turns out that the mass with a linear density function is just the integral as your x value shifts from one place to another of your density. Oops, it's not a p, it's a rho of your density function. Density function is a function of x. The dx is kind of like multiplying it by your x. We don't need an extra one. So that's just the idea of linear density. Pretty straightforward. And so the application would be like a wire, if we assume each cross-section is one. All right, so we'll look at an example of that in a minute. I want to take a quick look at radial density. Sloppy B right there. So radial density is where you have these, you imagine these circular, and they're just concentric circles. And the idea with radial density is that the density is uniform over each concentric circle, okay? But it could be different at this radius than that radius over there. Yeah.
So is it just going to be kind of like the linear density
and just, yeah, spinning it into a circle, right? So kind of like the shells that we did, but we're just looking down on a plate to do it. Yeah. So what happens is, for this, label, maybe this one right here, the density is rho 1, and the density over that one's a little bit different. We'll call that a different rho. That's going to be like rho 2. So if I wanted to know what's going on over that whole disk right there, well, to get around a circle like that, I need to know what its radius is, right? And so let's call the radius x here. So to spin around that circumference, that would just be 2 pi times whatever the x value is. And then we just multiply that by the density for that particular x value. So that would give me one of these coming around there. And if I want to add them all up to find the total mass, that would just be the integral as x goes from a to b. In this case, I probably have a be 0, but it could be like a washer type object instead. So I'd have 2 pi x rho of x dx. And that's radial density. A little more complicated than linear density. And again, the assumption of radial density is that each concentric circle has uniform density. If they didn't, then we'd have to integrate with respect to x and integrate with respect to y, a two-dimensional function, which that's like Calc 4. Do that, yeah. All right, so let's look at a density for a radial function. Suppose we had a plate whose density function is, let's say, radial density function, be more specific, is rho of x equals 1 over x. So if you imagine density like thickness, which in this case is not quite what I mean by it, right? That's the function 1 over x. So when we're at 1, the density of that ring would be 1. If we were at x equals 2, the density there would be 1/2. Right? So the density is shrinking as we go out. Okay. Now, here I'm not going to be able to integrate from 0 onward, because if I try to plug in 0, I get infinite density, which can't happen. So I'm just going to imagine that this is a plate with a little hole in the middle, so I have this washer. And let's suppose that we're going to start integrating at 1 with this density function, and then let's go out to 3. So what I want to know is on this plate here, what's the mass of the whole thing? All right, so it's going to be more dense over here and less dense out on the edge. So for radial density, the mass is just going to be the integral of 2 pi times x, right? These concentric circles times your density function, in this case 1 over x dx. And here we're letting x go from 1 to 3. And again, the hard part on these is deciding what formula to use, setting it up. Now this is pretty easy from here. What's our integrand going to be? Just 2 pi, which I could pull out. So I could say the mass here is then just going to be 2 pi times the integral of 1 dx from 1 to 3. Antiderivative of 1. So this would be equal to 2 pi bracket. And let x go from 1 to 3. 3 minus 1 is 2 on a good day. So the mass of this object right here would be 4 pi, given that radial density function. All right, so because we have to overly simplify density, it's not that hard. But it gets wicked hard, wicked fast if you try to branch into other dimensions, which we're not going to do today. I'm so sorry. But take Calc 4 if you're really, really curious. Next topic. Work. All right, so the definition of work is force, force with C, times distance. So for example, here's me, and I am going to push this box, and the box has something in it, like maybe a small child is hiding in it. And I'm going to push it that way, right? I have to apply some force to it to push it. Okay? As I move along, I'm working. If that's a big, small child, I'm going to start, maybe working up a sweat, right? You with me? So the amount of force I apply times the distance. Now, this equation works great if the force is constant. Okay? So if I have that constant force, as long as I can overcome friction, I can just move that thing along, holding that constant force. Now, most things don't. Oh shit! I moved my screen thing.
Whoa.
Let's see if I mess it up too bad. Yes. Okay, sorry, I got to reorient here. All right, so really, what happens in reality is force is variable. If you think about like overcoming a friction force, at first you start pushing and nothing's happening, and you push harder, and all of a sudden you break the friction and it starts moving. Right? If you maintain that force that was enough to break the friction, yeah, that constant force will keep it moving. But if you back your force off to below what it took to move it beyond that static friction state, then it's going to stop again. Okay. So if the force is variable, right? So if the force happens to be some function of x, then basically we're going to have to just kind of add up those forces over time. Okay. So here I have some little section that I'm going to push this through, right, called delta x. So I just want to apply that force, so I'm just going to get a change in work. Delta x is a very little tiny distance, but I got to get from one place to another to actually have a delta x. So if I wanted to know how much work happened over that little tiny distance right there, wouldn't I just take my force function and multiply it by that distance? Force times distance there. And then if I want to get the total force, then I would just add all of those up. Right? Now, we could add them all up, or we could do something else. What's going to happen is I let that distance get smaller and smaller and smaller, turn into an integral. Well, the distance is going to go to 0, but the sum is going to turn into an integral, right? So as we let delta x go to 0, which means I'm going to have more and more intervals, the number of intervals is going to infinity, right? Then I'm going to end up with an integral. So it turns out if you have a variable force, and you know the force function over whatever distance you're moving through, and usually we say x is the distance we're moving through, and it turns out the work that's done is just the integral of that variable force over your distance, from wherever you start to wherever you end. Just the integral of the force function. All right, so some more information. So we know what work is now. Work is force times distance, but what is force? Force is usually considered to be mass. Oops, that's an M. Times acceleration. It's a really heavy mass because it has an extra S. Again. So usually we just abbreviate that as F equals M times A. Now we usually say the mass is constant. Okay, so that means the acceleration could vary. So acceleration just means you're just changing the speed. So if the acceleration is constant, it's pretty straightforward. Like, for example, we consider gravity to have a constant force of acceleration, right? So that's a measurement that relates to really sea level, because the farther away you get from the Earth, gravity's force diminishes a little bit. We ignore that because the distances we travel up and down as a human being compared to the radius of the Earth is pretty negligible. So gravity is a good example of force equals mass times acceleration. Other thing that we need to know here is mass versus weight. Weight is actually a force. And force is mass times acceleration. So basically what that tells us is weight is dependent upon gravity. Mass, it doesn't matter. Okay? So if my mass is 70 kilograms, I'm still going to be exactly 70 kilograms on the moon if you throw me up there right now. Okay? But my weight will be different because the gravity on the moon is different. Okay? Acceleration on Earth, usually we have mass is measured in kilograms. Acceleration is usually measured in meters per second, which turns out to be the strange meters per square second. Okay. So what does it mean to be square seconds? Well, that's kind of weird. But what is meters per second a measure of? Speed, right? So acceleration is just change in speed over time. Okay. Whereas speed is change in distance over time. So it's just, the squared second just means you looked at two things change that were related to each other. Common units of force, in this case, would be, using the metric system, kilograms for mass, meters per second squared for acceleration. And that right there is called a Newton. So you'll see an N appear sometimes, and that's for a Newton. And by the way, I will give you a physics cheat sheet for the test.
Sweet.
Because we don't all have the same physics background. That's one reason I'm giving that survey, to figure out how much stuff to put in the cheat sheet. Because if it's too big, it's going to be overwhelming. And if it's too small, it's not going to help some of you. All right, so Newton is going to be a unit. So sometimes we talk about kilograms versus pounds. Those aren't directly relatable because kilogram is mass and pounds is force, which is different. So it turns out pounds are related to newtons, not kilograms. So I will avoid wherever possible using the imperial system because it kind of sucks. Other thing, if we put this together with work, what is work again?
Force times distance.
Force times distance, so force times distance. So with force, I have a Newton as my measurement, right?
Mhm.
With distance, if I'm going to be in the metric system, I'm probably going to use meters. So work is measured in Newton meters. Does anybody know what a Newton meter is that took physics? A joule, yeah. A Newton meter will abbreviate with the letter J. That's one of the units to measure work. And a J stands for a joule.
O-U-L-E,
Did
yes.
I get that right?
I think it's OU.
OU? All right. Thank you for correcting that spelling. That looks better, yeah. So joules is the unit of work. And so sometimes a homework problem will say, hey, this work situation is going on, state your answer in joules. What that means is you need to make sure that your units were meters, kilograms, and your standard meter per second.
Squared.
Squared, yeah. Okay. So let's apply some principles of force to work. All right.
There's a fancy integral for force.
Oh, I didn't get to that yet?
No, you did not get to that yet. Got distracted.
Oh, I did work. Yeah, so work is the, work is the main thing we're concerned about, and we'll have a force function when we do that. As far as an integral for force, that would be related to how acceleration might change, because typically we consider the mass to be constant. And we're not going to be looking at those problems. Good question. All right, so let's suppose I have to lift a stone. Lift a 6 kilogram stone 1 meter. Maybe we were building a wall and we had to pick that stone up off the ground, lift it up a meter and put it on top of the stone wall that we're building. How much work does this take? All right, well, let's see. We want to do work. Work is equal to force times distance. So let's see, what do we know so far? We have a meter, so we have a distance. Force, let's see, I don't have a force yet, because a kilogram is a unit of mass, not a unit of force. So let's see, what's resisting me when I lift that rock?
Gravity.
It's really gravity that's resisting me, so I'm working against gravity. And gravity has a force of about negative 9.8 meters per second squared around sea level. Okay, so that's gravity pulling down. So I'm pulling up opposing gravity, so guess what my force is going to be to lift that rock?
Gravity.
It's going to be the constant due to gravity at sea level. Okay, so let's see, force equals mass times acceleration. And, oops, I lied. I called that a force right there. What are the units here for? Which is acceleration, yeah. So I lied over here. That's the acceleration due to gravity, A. Sorry about that. The mass involved is the stone. So the force here is going to be the mass, 6 kilograms, times the force, 9.8 meters per second squared.
Does it have to be negative?
Since I'm doing the lifting, no, because I'm resisting gravity. So that's the force involved here. And because we're not moving far compared to the radius of the Earth, that force is not going to change considerably, measurably for us. We can't tell the difference, right? The distance I have to do, well, for my work, it's force times distance. And when we talked about this earlier, our distance was that little change in x, okay? And x here is going to be my height in this case. All right, so putting that all together, the work I'm going to do total is going to be the integral from 0 to 1 of 6 times 9.8 dx. Now, I just want to double check my units are working out okay here. And that's one reason I explained some of the units earlier. So the 6 is measured in kilograms. The 9.8 is measured in meters per second squared. And then dx is a little bitty x value. What's x going to be measured in here? X is measured in meters. So now I have kilogram meter per second squared, which is a, kilogram meter per second squared is a Newton, but I also have multiplied by, another meter. So now I have Newton meters, which is a joule, and a joule is a measurement of work. Okay. So all those definitions were important, and that's going to be on the cheat sheet. So I think I have the right integral set up because it has the right units based on the given information.
Will you mark us wrong if you don't write the integral down?
What's that? If you don't write the integral symbol down? Yes, that would be incorrect. Because we have to span the distance. Okay. And if you think about it, as we move that rock, we're doing more and more work, which means you're expending more and more energy, and you're going to feel it. Okay, so the integral is super important there. What's an antiderivative for a constant?
X.
X, right? So the 6 times 9.8 is just chilling out. And we just have x as we go from 0 to 1.
So 1.
So 1. So in the end, whatever 6 times 9.8 is, let's look that up. It's going to be, what, around 60. 50 something. 58.8 according to my Google calculator. So then I get the work done in this case. I'm going to have to, I guess I can squeeze it here, is 58.8. And the question is probably going to be looking for joules. Okay, so you want to make sure that you combine enough stuff to end up with joules in the end, which I was kind of double checking along the way. Not too bad? Question? We have 1 minute left. Oh, that means we are out of time for fun with math today. All right, so next class, we're going to do some more complicated problems with work, and then we're going to take a look at pressure, which is the third topic in this section. If you haven't done that quiz already, about half of you already have, please get that quiz done as soon as possible. Officially, the due date is the end of this week, but I would appreciate it if you get it to me sooner because we're moving on to new stuff over the next few days.
I take it that pressures can be measured in atmospheres.
Yes. Yeah, and since I only do physics once a year when I teach this class, that's another reason you guys get a cheat sheet, because I need one too, as a reminder of all these different units.
We did this in chemistry.
Oh, you did some of this in chemistry? I should stop broadcast.